Normal probability distribution. Sometimes we call this standard normal distribution. You might hear this standard normal distribution. Well, what's a normal standard or a standard normal distribution or normal probability distribution looks like? There's 3 criteria for that. Condition number 1 has a funny shape. What kind of a shape? Bell shape, yes. It's a graph. Is bell shape. Now, normally any experiment, if you do it the right way, fair, and you have a large sample of that, it comes out looking like bell shape. Now, if you want to see that, go to Boston Science Museum. One of the experiments they do there, and they do it probably about 100 times a day, they have a board that looks like this. It's a good sized board, about meter by meter, wide, about a meter height, and have these piece of wood pegs sticking out of the wall. And the front is glass, you get to see through it. And they have them like this. On the bottom it's in the holes there, and it goes all the way through, all the way to the bottom. Then the next one, they take these marbles, about 500 marbles, 1,000 marbles, and they dump them on the top there. Then you'll see them falling. Well, what happens as they fall, they hit these pegs and they bounce. Some will come down this way, some will hit this, bounce that way. And you'll see them going all the direction. By the time when they're done with it, if you look at the marbles, when they settle, they always have that shape. Every single time. And they repeat that. I stood there watching this probably 10 times. And every time they dump them, everything falls where it's supposed to fall. The reason? It is random. We didn't dump them in that corner, we dump them in the top, and they all spread as they come down. The spacing between these are the same. They're all round ones, not one side like direct them to go in different direction. Nope, it was fair. And you get to see them. It always has that bell shape to it, every single time. So that's a standard normal distribution. It has a bell shape. The other thing is, when you have a normal distribution, the mean always equals to 0. So mu equals 0. And the other criteria for it, when you have a normal distribution, the standard deviation always a 1. So sigma equals 1. So any normal distribution will have the bell shape. Now, when I talked about the Boston Science Museum, we are using discrete, bless you, discrete. Because we're using marbles. That's a discrete number, counting numbers. If you deal with a continuous one, like milk, every day you measure how many milks you get from that cow, particular cow, every single day. You measure and add them, and you graph that, you'll see that graph will look like normal distribution, just like this. Now, what we know about this function, this graph, is called the density curve. So let's talk about that graph there, that bell shape. We call that the density curve. If you take the area under that from negative infinity to infinity, if you calculate the entire area under that to be a valid one, it has to equal what? So the area under that anyone? Has to be 1. Must equal one. Well, since the area is a 1, when you think about probability, when you add all the probabilities, like we did this table, in the last video, we did the table of people over the age of 62 wearing sunglasses. If you add all these probability, that sum should be what? 1. Interesting. When you add all the possibility, the sum is 1. When you find the area here under the curve, the answer is 1. That tells me what? There has to be a correspondence between the area of this and the probability. It has to be something connecting them. This actually graph really represents the probability of an experiment. So the fact the area is 1, and when you add all the combination, that's a 1. There's a correspondence between this and the probability. We'll bring that shortly, but I'm just bringing that up. So the area under that's always a 1. If you take a knife and you slice this in half, it should be what? And you fold them, what you should notice about the two graphs? Symmetric. Should be symmetric. And again, as I said, there is, I don't care how you slice it, there is a correspondence between the area and the probability. So there's a few things about that curve. Does every experiment look like normal distribution? Well, sometimes things doesn't fit exactly the way we like to see them. We like to see everyone looks like this. Well, let's say we did this experiment, but the result were uniform. I'll wait till you finish writing. Let's take a 9-volt battery. I'm just thinking of something off the top of my head. A 9-volt battery is supposed to have a voltage what? 9 volt. Do they always have 9 volt? No. So when you get a 9-volt battery, try to make it nice and neat. We measure a few of them. We found actually the voltage for a 9-volt battery doesn't really, it's not always 9. It's somewhere between, I don't know, 8.9 volts and, I don't know, 9 point what? 2? Okay, 9.2. I'll take that. So we find out all the batteries that we make are between 8.9 and 9.2. And we found that it is uniform. Uniform means they all have almost the same height. So given the uniform, the word uniform tells you it's not a bell shape, it's constant value. Given the uniform, I don't know, graph, illustration, whatever you want to call it, what should we call it? Find the probability of a selected battery, I don't know, which has a voltage greater than 9.1 volts. What's the chance if we select a battery will have a voltage greater than 9.1 volt? Well, where's the 9.1? Right here. So we're saying, what is the chance? We're saying this graph corresponds to a probability. So what is the chance? What's this area equal to? Because that corresponds to the probability. Well, if I know what the height of this light, or this line, not light, if I know the height of this line, I can tell you actually what the area there is. Well, how high this line should be? What's the height here should be? Since the whole thing's supposed to be 1, the entire area should be 1. The height of that should be what? 1 equals the distance from here to there, which is what? 9.2 minus 8.9, that's the distance, times the height. What is 9.2 minus 8.9? Is that 0.3? So what's the height equal to? 1 over 0.3. 10 over 3. So what is the probability? What's the chance if we select a battery, that battery will be greater than 9.1 volt? Greater than 9.1. Well, what's the size of, what's this area here? Well, that's equal to what? The width times the height. What's the width? Isn't that 0.1? From here to there, isn't that 0.1? Yeah. And what's the height? 10 over 3. 0.1 is 1 over 10 times 10 over 3. What's the answer? 1/3. What's the chance if we select a battery at random, that battery will have a voltage greater than 9.1 volt? And this one says 1/3. 1/3 of the batteries that we make has a voltage higher than 9.1 volt. As I said, it's not often you see something like this, a graph that has uniform value, constant value. Normally you have bell shape. We're going to do the standard normal distribution. Next class we'll continue with the bell shape and show you how we find the probability of different value. And I don't know if you remember when we start talking about probability. Remember I threw three statements there. I said what? 67% of the people land within what? 1 standard deviation. 95% of the people within what? 2 standard deviation. 99.7% within 3 standard deviation. I'm going to prove that next class, where the math came from. It's not just me making these numbers. The math will show you where we came up with these numbers. So I'll wait on that video, and we'll continue more with normal distribution.